We should start. Everybody must be having lunch, a long lunch. So the first speaker is Ismail Davila. He's a master student in mechatronics engineering at Victoria's Polytechnic University in Tamaulipas State in Mexico. And he's working on machine learning classificators implemented in FPGAs for citrus fruit grading automatic machines.
Yeah. Thank you. Hey everyone, I'm Ismail, and this is my project. So the topic is decision tree-based pixel classification for real-time citrus segmentation on FPGA. So this is the outline that we will see. Just a pretty easy introduction, and then the proposed architecture of the project, and then some results, and the conclusions and future work. First of all, the orange production in Mexico is huge, and according to the Food and Agriculture Organization, Mexico is in the top 5 of the orange producers in the world. Also, Tamaulipas, that is my hometown, it's the second citrus producer in Mexico. This is Tamaulipas state, and only in 1211, the total production was approximately 500,000 tons of orange. So, for these quantities, automatic fruit grading systems are needed. So, in this graph, the orange offer and demand is shown. Mexico orange production, the expectation in 2020 is about to 8 million of tons. So that's a huge production, and also the world importations are about 13 million of tons. So this is according to the Mexico Ministry of Agriculture and Rural Development. So as we know, the computer vision and machine learning, computer vision is the process of understanding digital images, and the machine learning is a subset of artificial intelligence, and it stores algorithms. So this is only for perform tasks without an explicit instruction, right? So the decision trees are a powerful computer machine learning tool for achieving automatic tasks. So the proposal is, the main problem is to bring a large amount of citrus fruit, and the first stage to solve this is the segmentation. Our solution is to make or build an automatic grading machine based on a computer vision, machine learning model, plus an FPGA. And why a machine learning model? Because it's flexible and can be modified for other tasks. You can get another features to train it, and you can use it for any other task you want. So, why the FPGA implementation advantages? Because, as we know, it has a reduced power consumption. Also, it's real-time responsive, and also the hardware has a reduced dimension, and also we can introduce or instantiate multiple processing lines with one device and work all of them in parallel. And this is the system overview. So the first device we see is the camera, and it has an HDMI output, and it's connected to the FPGA that will be the image processor. Also, microcontroller is connected to the FPGA to make, and the microcontroller is sensor and actuator manager. It's just acting like that, and there is some server board to communicate each other. Also, It's only for debugging and measuring a device. This capture is not part of the final hardware of the project. And also the output is connected to a display to check, just to check some information there. This is the project platform. So we see it's a machine with some rails, and right now the setup of this is to bring some oranges in the rail, and the oranges will loop on the rails. This is the main rail. This is a dark cabin that the video processing will be done, and this is just a loop to make them passing through the camera. In this part, there is a rail that pushes the oranges through this part. So here's the dark cabin. If you check the setup, is the industrial camera with HDMI output, and also it has some lighting here. If you see here, this is closed because we need a controlled environment. So also you see the rollers are in black, also the background is in black. So that will be a user segmentation. Here we can see the hardware components that we used. An 18 mega microcontroller, an user camera. This is the capture that we used, and this is the FPGA that is called Industrial Video Processing Kit that has attached on Spartan 6 FPGA from Xilinx. And the hardware components that we used, the principal components are Weka for feature analysis and generate the model. Also, Python was used for feature analysis, but the most part was for text parsing. Also, OpenCV for image processing and data acquisitions, and Xilinx ISE for HL synthesis and hardware development. Here is the methodology that we follow. In the first stage, we have a PC stage. That was for generating the digital twin model. So first of all, we get a data set only of orange images. After that, we got the segmentation for segmenting the oranges in the PC stage. After that, we convert some features to another features. Here in the feature section, convert the RGB to HSB and also the grayscale channel. Then we got another data set only of pixels. After that was done feature relevance analysis to check which channels were better to build the model. Then we get a model generation with Weka, and we train it to check its performance. Also, we have a second stage, that is the FPGA stage. These are the models that are part of the system. First of all, is a pixel buffer that it only handles the data, all pixels that are coming from the camera. Also, HSB and grayscale conversions. Then the decision tree segmentation module. Then some morphological operations to get better results at the output, and then draw the segmentation for the input image. Then was done an integration to, first of all, recording the results from the FPGA. The result, and this was done by the capturer. to make some comparison and measurements of the segmentation. The comparison will be done by the PC segmentation and the FPGA segmentation. First of all, the dataset, like I said, this is a processor. First of all, we took we record some videos of the system, and then we got a region of interest that is called void, and that images are cropped for the dataset. After that was done basically segmentation, then the center detection for take the dataset. And also was done a script to take all the images automatically. Then manual image classification, because in a future work, this work is a previous stage of classification of color and size. So this was done too. Then was the feature extraction that will be explained. The following sections, and then the pixel data section. So here is the sample frame that we got in front of the camera. If you see, this is the orange direction flow. So all the oranges will be passing from the right to left. Then you see this part is kind of red. So this is the PC segmentation. Also, you see here the center that will be useful for this snapshot threshold. What is this? This area you see here is a snapshot threshold. Once the center gets the snapshot threshold, the frame will be taken only once to get the orange images. And so also you can see here the void, that it's a window of 600 pixels by 600 pixels. After taking the dataset of oranges, if you see this sample input, after taking all the inputs, then each feature was extracted from the image. So here we have a sample frame. And if you see, this will be these columns. For each pixel, this will be the data set. Then it is converted to another color spaces. And you'll see here that is HSB and gray channels that are also here. And also the segmentation done by PC. So if you see, we only have two classes, that is a non-segmented pixel and a segmented pixel. So if you wrap all of them in a matrix, you will get a data set of pixels. Then a feature relevance analysis for check the base channels. And you see, we use these tools. And after that was, this is the main topic of the project, was to make a script in Python that is called Decision Tree HDL Builder. Okay, this you see here. First of all, we got the dataset only in pixels, right? Then we trained the model, yeah, with Weka. Weka, the output of Weka is only a text file. So with this text file, it's the input of the script. So this is a text file. So this script will analyze the text to make a decision tree in Howard. So the output will be a decision tree model that is written in VHDL. So here's a Howard architecture that is pretty simple. If you see, the pixel buffer only handles the timing signals, and also the pixel that it's incoming. And also there is another pixel buffer in the output to maintain the same video signals. And here is the grayscale conversion model and the HV conversion model. All these models are combinational circuits. And after that, there is a segmentation model that has here is a segmentation, the output, and this MOM is the morphological operations model. You see only MOM and the pixel buffers are synced by the video signals. And after that, the mask driver will draw the segmentation output. So here is the morphological operations module. That is, it's only a big buffer. If you see, this is the image. This is the image of this resolution. And this image is not in RGB. Remember that this image is only a segmentation. So in which the other words, it was declared that each pixel was only 1 bit, right? So in the buffers, we can handle a lot of bits. And it's pretty, the model is not huge. So you can see here the window and the raw buffers that we have to store all these bits to process the window plus the structural element and then make a morphological operation. If you see, this is the incoming bit, so each clock cycle it's stored a new bit in the window, and this will be sliding out of the image. And also the morphological operation will be, the output will be 1 or 0 depending on the morphological operation was done. So here is the mask driver module, and if you see here in the output we have an RGB image, and then we have the segmentation. So if you combine these two images, we get this, that the segmentation will be drawn in cyan color in the output. Also, you can see here that it's some color, so it's just the segmentation is drawn in a cyan color here. After that, what's done the segmentation model? Okay, let's describe this. And the segmentation model, as I said, was done by the Fusion 3 HDR builder. It only classified 2 classes, and this approach has the following advantages. It gives approximately the same combinational path, because how the architecture was generated. Also, largely can be handled because it uses a very low amount of resources. Also, the trip depth is not significantly because it only needs comparators in parallel. So here is a little example about what is Fusion 3. So x1, x2, and x3 are the features. And if you see, the continuous line is an if statement, and the dotted line is an else statement. So we have to build this in hardware. And this approach is an easy hardware implementation because you only use comparators, since you only have to compare the feature to a threshold versus a threshold. And it not uses complex arithmetic operations because it's only comparators, and it's not resource expensive and can be solved as parallel circuit. And let's see the algorithm. So here we have an example of the Fusion 3. The output of Weka looks like this, right? So the first thing here, if you see the line 1 and the line 6, the line 1 is an if statement, and it's comparing the feature 1 with this threshold, with this number. And if you see, the else statement is in the line 6. So the first stage of the algorithm is to look for all the outputs that would be 1, like in the line 5 and in the line 6. All the branches that in the output would be 1. So if you see here in the line 6, we have the output of 1. So to solve this branch is pretty easy, because only we have to compare the first feature with this number, like this, and we need the else statement. So we only have to use a NOT gate there. Then to solve the branch of the line 5, you have to solve all the steps. So first of all, we need to solve this stage. So it's here it is solved, right? Then we need the else statement of this comparator. So we have to connect another NOT gate. And for at last, we have another else statement of this comparator. So we only have to connect another NOT in the output of the comparator. All the branches should be grabbed in an AND gate. Then all the branches that the output is 1 are wrapped in our gate. That's how the mind works. So here we have the results. First of all, we recorded some 9 videos with different speeds. As you see here, OPS means oranges per second. And if you see, we recorded 9 videos from here. And from the videos was taken this amount of images, also the same amount of segmented oranges. Then here is the pixel data acquisition, and we got that amount of pixels. If you see, it's not a very large data set because all duplicated pixels were removed. Here is a feature relevance analysis, and if you see in bold are all numbers, most of all analysis points to gray and green channels that are the best features. Then the team model training, 3 models were built with this, with using different combinations. The first one was gray IQ. Why the H channel? Because it's known that the H channel is good for colors. Then gray and green to test its performance, and then with all the features. So if you see, the testing of Weka was the M4 was the best model. And if you see here, if you see only M1, M3, and M5 has morphological operators in the output to get a better performance. So if you see, the kernel size was 7 by 7, and also you can see that the morphological operation was the close of delayed functions. And here we see the segmentation. Here's a sample frame. And also you can see that M2 has the best performance. If you see here, in M4 has a lot of porosity. And also same for M0. And with the morphological operations, we get non-porosity. But it's not a big deal with M2 and M3. There's no significant difference. So here's the Tushano algorithm comparison. Here's the species segmentation, and then the FPGA segmentation. And these all pixels in white are the error. That's how the error was measured on the accuracy. Also, we got some troubles there because we got some shifting frames because this was automatically taken by script. So we got some shifting frames, and these frames were discarded for the results. So that's why here we have a different amount of samples, and as we see in M2 had the other performance. Also, if you see in M0 and M4 has this accuracy, and then with some logical operations we get a better performance. As you see in M5 and M1. And these were the model resource usage. If you see, every model used approximately the same amount of FPGA resources. In conclusion, the experiment showed that the DT model implemented on FPGA is able to perform image segmentation in real time. Also, the feature relevance analysis allowed us to find the best features and find the best model too. Also, the proposed decision tree model is very few resources, and we can attach another module and maybe process in parallel 2 lines. Also, let me remind you that this work is not just how to detect defects in oranges. This will be addressed for our future work with using infrared sensors. And also, this is a previous stage of orange and color size classification. And the proposed architecture shows that the system is able to segment 5 LPS. That this velocity is the same of 1 foot tone in approximately 80 minutes. Let me give some acknowledgements to Panasit under the research grant, and also for these companies, Electrónica Automatización del Noreste and Red Company. Let's visit the webpage. Thank you. I will show you some videos. So this is the machine on runtime. So there you can see the output of this is not the output of the FPGA, but there you can see the oranges passing the loop, right? Here is the segmentation on real time. This is in the maximum velocity, right? And also, once the classification is done, we are making those actuators to push the oranges out of the loop. And that's it. Thank you for coming.
So, are there any questions for the speaker? No questions? Yeah, I have a question. So, you said you used the decision tree model for classification. Why did you specifically use the decision tree model? Did you compare it with other classification models?
Yeah, because it's pretty simple. That's why.
Oh, it is.
It's simple because you don't have to use any complex operators like multiply or others like that.
And also, you said you are going to use machine learning. So
yeah, the machine learning part is once the model is trained. here. So here in this stage is used Weka for train the model. The Weka will output the machine train model. So that is part of machine learning stuff.
Any more questions? No? Okay. Thank you. So the next speaker is Keaton Stockey. Is a computer engineering master student at the University of Arkansas, and he will be completing his degree in May, and he works in computer systems design laboratory under Dr. David Andrews, and spent his time researching FPGA systems